Hello students, welcome to TSS Tutorial Center, where we make complicated topics very simple to understand. So if you are under natural and applied sciences and you want to become good, you want to become better, you want to start thinking outside the box, then do subscribe to this channel, because we break down complicated topics to something which you're going to understand in just a short period of time. Fima Zwibo! Zwibo dude. In this tutorial, we talk about deformation of solids, which is coming from physics. Let's dive into it. Okay, so we're supposed to know what it means when someone says deformation of solids. Now, before we talk about that, it is worth mentioning that a solid is able to compress and also to stretch. To compress is to change in length. It decreases in size. Then to stretch, it means to increase in size. That is the ability of the solid. It's able to compress and also to stretch. Now, the word deform means to change in size or shape of an object. Now we're talking about solids and deformation of solids. So we might define deformation of solids as the change in size or shape of an object when a force is applied to it. So it's going to change its shape or size when force is applied to it. Okay, this is what we're talking about. Now, to understand deformation of solids very much good, you're supposed to know the just simple terms which are used. They're just very simple. You can even understand just by looking at the word. Okay, so we'll start with stress. What does it mean when someone says, I'm stressed? To be stressed is the internal force which is going to be applied over a given area. I used to define stress as the internal resistance of the material to deform when a force is applied to it over a given area. But I found it simple actually to define it as the internal force applied on an object over a given area. Now, since we are saying stress is the internal force over a given area, in some words, it is force per area. And this is how we are going to be calculating it. But we're going to explain much more. First of all, let's just talk about the terms which are used. So we are saying stress, this is the internal resistance of the material to deform when a force is applied to it over a given area. We can say this is the internal force applied on an object per unit area. Very simple. What else? You're supposed to know what it means when someone says strain. Strain. What is strain? Actually, it's very simple. And if you're asked such a question, then you're supposed to smile before you even answer the question. It's the change. It's the ratio of change in length divided by the initial length. Is the ratio of change in length to initial length. Now, since we're talking about the ratio, is it going to have units or it will have no units? A ratio doesn't have units, but a constant might or might not have units. Elastic material. What does it mean? What is an elastic material? Very simple. Elastic material is a material which is able to come back to its normal size or shape when a force is applied to it. Or you might say is a material which can be compressed or stretched when a force is applied to it. It comes back to its normal or the original shape. Then we'll talk much about this guy. Have you ever heard of Robert Hooke's law? Okay, so we'll talk much about this one. Hooke's law. What does it state first of all? It states that the force applied on an object, the force which is applied on an object is directly proportional to the extension provided the elastic limit is not exceeded. We'll come and explain. Now I just want to, if you can be writing this, then it will be very much good. Then we'll come and explain what they really mean. Now we are saying proportional to the extension. What is extension? Force, we know this is the pull or push exerted on an object. Now what is extension? Extension is just the change in length. Okay, so we are done with the terms which are used. Let's go now to the main explanation. Okay, so we'll start with Hooke's law. Like we said, we're gonna talk about Hooke's law. Okay, so do you remember what we said? We said force is directly proportional. Is it directly proportional? If you have forgotten, we said force is directly proportional to the extension, provided the elastic limit is not exceeded. You are but when it is exceeded. I'm saying when it's not exceeded. Fire in the name of Jesus. Now it's given by what? So what we are saying is this. We are saying force is directly proportional to what? To the extension, the change in length. When I remove the proportionality, I'm going to have a constant. It's not a ratio, it's a constant, which is called the stiffness constant. Now, this is the formula which explains Hooke's law, where F is the force, X is the displacement, or you can just say the extension, and K is the stiffness constant. Very simple. So why are we saying the stiffness constant? Because the value of K is going to be telling us how stiff the object we are dealing with is. For example, suppose you have an object with the value of K being 200 and the other one to be 100. Now, does it have units? It's a constant, it's not a ratio. So you can definitely make it the subject from this equation. Let's make K the subject. It will be force divided by what? X. Then force is in newtons. Extension change in length. Length is in what? Meters. So we're going to have Newton per watt per meter. Even here it will be Newton per watt per meter. So this one, since it is greater compared to this one, so the object which is going to have 200 will be very stiff. We're supposed to apply a lot of force to stretch or to compress it. Okay, that's what it means when you're talking about what? The value of K. It determines how stiff the object is going to be. Let's move on from there. Now, suppose we have a cylinder. Okay. Suppose we have a cylinder. Let me get the cylinder, this one. Then I apply a force on top there. Let's call it F. What do you think is going to happen to it when I apply a force on top there? It will actually start decreasing in what? Length. Let's call the initial length as then when I apply a force on top here, this material, this cylinder, will start doing what? Decreasing in what? In size. So it will become somewhere there, which means the length has changed. To find that length, change in length, this is known as delta. This triangle thing is called the delta hint. It means change in. Now we're talking about length, so it will be change in length. It will be L minus L initial. Now it is worth mentioning that when you are compressing, the change in length is going to be negative. When you are stretching, it is increasing in size. The change in length is going to be what? Positive. We can prove this. Since it was decreasing in size, this value, the first one, is going to be greater than 10. We're just supposing you are going to subtract 10 minus 20. It's going to give you negative 10. But if at all we were stretching, then actually the value that we're going to get is going to be what? Positive. Yeah, this is what we're talking about. Now, considering the cylinder to be elastic, what do you think is going to happen when we remove the force from it? It will actually get back to its normal size. Now, what did you note? What did you take note of when we're talking about this? The more force we apply, the more the object is going to be what? Compressing. Okay, that's why we are saying that force is directly proportional to the extension, because when we increase the force, the more extension we're going to do what? To have. And this is where now the formula came from. Okay, now let's talk about stress. Now we talk about the formula. Does it have units? Yes, it does. It does have units, and we're going to talk about those units. The bar bar bantu bar monarcha bar promoter. Okay, so according to what we said stress is force per unit area. Do you remember? Yes, that's exactly the same things we said. Now, stress is denoted as sigma. This is the symbol for sigma. Now we're saying it's given by force divided by what? By the area. Very simple. That's the formula we're going to be using. Now, does it have units? Yes, it does. We're talking about force over what? Area. So the units are Newton per square meter. The units are Newton per square meter. Now, this is equal to Pascal. So it is worth mentioning that the SI unit for stress is just Pascal. Okay. So this is the formula. And the units are Pascal, as we have discussed. Now let's talk about the strain. Strain, which is the change in length divided by the initial length. Okay. Now, when you're talking about the strain, we said it has no ratio. Yes? It has no units because it is a ratio. Do you remember? Yes. Now, if you don't, and you want to confirm that this one has no units, strain is denoted as this kind of E. Kaya, the name you can give it. At the bat bantu ba monaka ba promoter. You have change in length, which is in meters. You also have the initial length, which is also in meters. So the metric units, they will be cancelling. They will be cancelled out. At the end, we're not going to have any units. So, in conclusion, we may say strain has no units. Okay, now do you remember we said when we are compressing, what is going to be the change in length? Is it going to be negative or positive? We said it's going to be negative when we are compressing, which means the strain is also going to be what? Negative. When we stretch, it means the change in length is going to be what? It's going to be positive. Exactly. So even the strain is going to be what? Positive. The bar bantu. Now let's talk about something very much interesting. Young's modulus. This is also known as elastic modulus. So you might hear some people saying elastic modulus. Don't even get confused, my dear. You know exactly what they are talking about. But I love using the word or the term Young's modulus. It sounds unique. Okay, so think about it. What is Young's modulus? Think about it. Okay, so whenever someone comes to you and tells you or ask you what is Young's modulus, just look at them. So I'm going to answer your question. So Young's modulus is the measure of how much an object resists to be compressed and to be stretched. It's the measure of how much an object resists to be deformed, in other words. Now, let me give you an example. Between a metal and let's say this is copper. It's big. And let's say this is copper, but it's very small. Which one do you think is going to be easy to bend? This one? Not so. So this one is going to have Young's modulus, which is low compared to this one. Okay, that's what we're talking about. This is the measure of how much an object resists to be compressed or stretched. Now, the same Young's modulus is given by stress over strain. The same things we are from talking about. So it's very much important to understand the introduction. Some of you like skipping the video. Make sure you understand where we started from. Thus, it will make it simple for you to understand where we're going. Okay. It's actually given by stress divided by strain. The Young's modulus, however, it can also be expressed in terms of force, the initial length, the change in length, the area in the area. Now, also, we talked about stress, which is given by what? Force divided by area. So I will substitute where I'm seeing stress, I will substitute force divided by area. Then what we talked about strain, we said it's given by initial length divided by what? It's given by change in length divided by the initial length. So I'll get the same units, substitute. So this is what we're going to have. Now, to simplify this, we're going to end up with this simple formula. If you don't understand where it's coming from, let me show you, my dear. I've just seen this equation here. Very much simple. It's saying elastic modulus is given by force divided by what? Area. Now this gamma guy here, we know that that's division, so we're dividing where we have change in length divided by initial length. Okay, what we'll do is we'll flip changes to multiplication. Initial length will go on top, and this guy will come there. This is where the formula is coming from. Very much simple. Now, does the elastic modulus have units? Do you think it have units? Yes, it has units. Look at this. We have elastic modulus. There is force, initial length, and we also have what? The area and the change in length. This guy and this guy will cancel. So end up with Newton per square meter, which is equivalent to Pascal. So even the SI unit for the Young's modulus is Pascal. Okay. This is what we're talking about. Now, for what is worth, let's try to make L the subject of the formula and understand what the formula means. I'm not going to waste much of my time on this. I'll be quick. We're going to make extension the subject of the formula. Okay, so making it the subject, we're going to have this. Now, what does this mean? So we have extension, which is delta L, is given by flow, I call it flow, over elastic modulus times the area. Okay. Now what does this mean? Have you seen that the force in the extension, they are occupying the same position? This is the numerator, even this one is the numerator. We talked about this, then it means they're directly proportional. So this one is directly proportional to this one, even this one is directly proportional to this one. When we increase the force, what do you think is going to happen to the extension? It will increase as well. That's where Hooke's law was coming from. Okay. Now, after you make force the subject, you should get this. So make sure you know how to make the subjects. Then lastly, this is not the last part, but we are almost finishing up with the explanation, and we'll do some questions. You're supposed to understand the graph of force versus extension. It's very much important. Okay, so force is going to be the y-axis and x is going to be our extension. So it will come up something like this. From here to there, we can see it's somehow more like a straight line. This line is known as the proportionality region. Proportionality region. Why is it known as the proportionality region? Because it obeys Hooke's law. It obeys Hooke's law. Now, from here we can see that this line has started changing. It is not that straight. It's not straight at all. But when we continue applying force to the object, it will reach at a point known as elastic limit. Somewhere there. This point is known as the elastic limit. And from this, before this point, this entire region is known as elastic region. Why? Because the object is going to come back to its normal or the original position. When you exceed the elastic limit, the object you are dealing with becomes more like a plastic. Think about it. If you have a plastic and you stretch it, the plastic, does it come back to its normal or the original shape? It doesn't. That's why this region is known as a plastic region. When you continue to apply the force, then the object will break. At that point where it's breaking, it's known as the breaking point. Very simple. Let's move on to something else. Work done. Okay, so you're supposed to know the formula, and you're supposed to also know how to drive the formula for work done. So we actually use the proportionality region from our graph. Okay, so we had the force to be the y-axis and the extension to be the x-axis. Okay, so this is the proportionality region. That's what we're going to use to explain what we're talking about. It is known that the work done is equal to the area of this triangle. Now if I ever ask you to give me the formula for the triangle, the area, can you fail? You still remember it's half BH. Okay, so the B is going to be the X and the height is going to be F. Okay, so the formula is going to be half HX. Now do remember, we've been talking about force and we've been saying that force is equal to Kx according to Hooke's law. So what are we going to do? I'm going to substitute the same force, and this gamma guy, the area, we are saying that is the work, so I'm going to substitute W where I'm seeing the work. So actually I'll end up with a formula which is very pretty. This formula, we're going to be using it a lot. When you start talking about simple harmonic motion, in my dear, don't even be frightened. It's very, very much simple and you shouldn't have to be scared. We'll come and talk about some formulas like this. This one, same concept on how to drive it. This one, we'll come and talk about it, how to drive it. It's very simple.